people, so I'm the same guy who made FlexPave, if you remember. I'm gonna just show it to you what it looks like. This software, if you remember, I gave this on YouTube a few months ago. So I made another one, something of the sorts of the same thing. It'll be fun, you'll watch it. So let's go and see what this thing's about. It's a useful tool for reinforced concrete analysis and design. So let's see. So in this presentation, in this entire video, what I'm going to do is I'm going to introduce you to Conc. The name's Conc, by the way. How to use it, how it works, what it gives you, and what it wants from you, by the way. So let's go ahead. What is Conc? Yeah, I know that's a strange name, but sure it's catchy, so yeah, it does serve a purpose. It is a software that's meant to give you the neutral axis, the moment, the factor, unfactor moment. You can see the unfactor moment here, the factor one here, the curvature of the strain diagram, the depth of neural axis, the centroid of the neural axis itself, and the strain in the tensile steel, the compression steel, and balance moment as well, if you want it. All directly by simply clicking one button. Now I know a lot of you people out there, civil engineers especially, will have a lot of problem with these things. For example, if SAP and ETABS does handle this, I know that, but it can be a lot of hassle if you want to change the cross section. For example, you want to change the tension steel area and wanted to find if your factor moment is up to par with what you want it to be. It can be a long process. This thing, on the other hand, gives you all of this stuff with one click of a button. We'll see that in a minute. How it works, it's the same sort of thing we used in FlexPave. We have a start page, a project page, and a calculation and saving page. This time I made the calculation and the saving page all to one page. You'll see it in a minute. So with the start page, you have the same stuff, or you can work on a new project, or you can open an old one. It's the same thing. So in essence, you have this XML file, which is saved in your own folder inside your documents folder. We'll go to that in a minute. I just want to introduce you to the interface and stuff in case you're new to the channel. So we have a project page here. What this does is basically it allows you to make any type of area. This, for example, is a rectangle. It has a width of 12 inches, meters, whatever you want to say, but I'd rather keep it in inches. Everything's in inches. If you're going to change anything, change it throughout the table. Change the modulus of elasticity. As a matter of fact, don't change anything, just keep it in inches. So we have a width of 12 inches and a depth of, it goes from 0 inches to 20 inches. Like, you've given the depth, total depth of the section is 20 inches, so you go from 0 to 20. You can change that. I'll give you an example in a while. So what we're doing here is that we're taking three types of shapes: a rectangle, a trapezoid, and a circle. So there's a lot of combinations that can come out of these three shapes. I mean, a lot of them. So that's we'll go to that in a minute. And once we get to that, the software needs about 6 inputs from you, which are obvious. I mean, distance to centroid, tensile steel. That's a lot of stuff that you already know about your beam. What you don't know about your beam are these things. So the software will do this for you. How it does it? It simply does one normal thing. It calculates the tension force inside your beam, which is the area of the tensile steel multiplied by the stress in the tensile steel. In this case, for example, 16 bit 60 is 360 kips. What the software does is that it starts from initial value of, for example, C, and increases or decreases the value of C to see if the tension force is equal to the compression force. In this case, 0.85 in FC prime and the beta C. Beta C is this darker shaded area, which is the total compression block from the Whitney stress block, remembering concrete courses. And this is the tension reinforcement, the force from the compression steel, if you understand all that stuff. Well, if you don't understand, what are you doing here? Also, this software, this time around, is going to give you three things. One, it's going to give you an Excel file, obviously, all the iterations. Another thing that it's going to give you is a report. is going to give you a report of all of these things you entered, plus the diagram and the outputs. I know a lot of you guys wanted to get that diagram last time, so here's another thing. And you can save this diagram with a good enough quality by simply clicking two buttons. I'll get into that. So without going any further, let's just get into how this thing works. So you double click on this and give you a little splash screen or whatever. And for example, this time around I want to make a new project, so I click this. And I go here. Now let's say my project, I want to give this name of, let's say tutorial. And model of elasticity for rebar in KSI is 20.5 in KSI, doesn't matter, that's enough. Total depth of the section, I want to make this 18 inches. And yield strength of the rebar, I want to make this 50 KSI. Extra notes, well, blah blah blah, whatever. Okay, then let's see, serial number one of our shapes, I want to make this a rectangle. So I want to make the width of the rectangle 12, which is 12. I want to take it from 0 to, let's say, 15, not more than that. Let's make it 10, just for the sake of the argument. And another shape, we can have 3 shapes in total: rectangle, trapezoid, and a circle. So I'm going to make this one a trapezoid. Next up, I'm going to make the top width of the trapezoid, which starts from 10, by the way, because I already have a shape at 10, and it goes all the way to 18. So I'm going to start with the top width of 12 and a bottom width of 24. Let's see what this looks like. Here we go. So this is here's the depiction diagram. Whatever you make here, you can redraw it and it's going to show up here. So just as first thing, I'm going to add another thing. There's also another thing that normally happens. For example, if we want a duct here, a duct or a pipe, whatever you want to call it, and it takes water, stuff like that, and you don't want it to be part of your analysis, you can subtract that area. Just click minus 12 minus. You're going to use the minus over here, no, or in case of trapezoid, in both of these columns. So if I want to make this a circle, let's make things interesting. A circle, and I want the circle to start from, let's suppose, 2 and go all the way to 6. What's going to happen? We get a diameter of 4, and since we're subtracting this area, it gives a coefficient of a minus. So let's see, we got a circle here, and this is going to be subtracted from our entire compression block. Let's see what happens next. When I click next, it gives me a few things that I need to enter. One, the area of tension steel in inch square. So let's say I want to make this 5, and it needs me to give area of compression steel in inch square. Oh, I'm going to make this 0.5, and it wants me to give it a distance to tensile steel in inches, obviously, because I gave the depth in inches. So now the total depth is 18 inches. Normally the distance to tensile steel centroid is about 2.5 inches less than the total depth, so I'm going to make this 15.5 inches. The same can be said for the compression steel. That's 2.5 already, so no need to change that. I'm going to go on and make this compressive strength concrete to 3 KSI. This is KSI. I'm going to change that. And what else does it need? Okay, this is tolerance. I'm going to explain this later. As for this, it needs an approximate for neutral axis C. It wants an initial of that starting value. What do you want to give it? So let's make this 8. Oh, here we go. Oh, so this is the entire equation it's going to be using for you to find the compression block. This is meant for you to verify it yourself in case you want to do that. But if you don't want to, that's cool. I click recalculate, and there you go. It already found out its stuff. So let's see what it's got here. One, it's got a ton of iterations. It started from 8, it increased it to 8.05. Let's see, the tension was 250, the compression was less. So it increased it by increasing the depth of the neutral axis. It's going down. It went from 8. 8 is somewhere around here it's supposed to be, so it came down. It keeps going down all the way till we have the compression block almost equal to the tension block. you can see another interesting thing going on here. The stress and tension block, we gave a, if you remember, we gave a yield strength of 50 ksi. It's decreasing. At a certain level, it goes less than 50 ksi tension steel. Let's see, where does it happen? Where does it happen? Where does it happen? It happens here. Here exactly, at iteration 118, when the neural axis goes to 9.845, the stress in the tension steel goes below 50, which means that it's not yielding, which means that it's not yielding. So that's an interesting thing. Another thing that we see is the diagram. So let's see, we have this blackened area, which is supposed to be the compression block. We have this red dot in the middle, which is supposed to be the center of the compression block. The centroid of the compression block, not the center. The centroid is something different. The centroid is meant to go towards the area that's, has more area towards it. For example, in this case, it's not exactly equal to half of this, because there's a circle here, and it's going to tilt towards the bottom a little more, not a lot. So there's that. And then we have the what's this? Oh, yeah, neutral axis. So it's not exactly a 10, but it's 9.86, somewhere around there. And then we have the tension reinforcement where it's present. We have the compression where it's present, and we have the strain in the concrete, which is obviously centered at 0.003. The strain in the compression steel, which is 0.0002, and the strain in the tension steel, which is 0.0017. Okay, interesting enough. There's another thing that you might notice. Let's see, the balanced steel area is 4.954, which is really close to 5, which means that this is the balanced steel. When you're giving this as the tension steel, the compression steel, if you remove this one, let's make the 0, we'll get a different type of steel, which is obviously not a good thing. Seeing this, well, whatever. We get a different type of steel, as you can see. So that's almost. So there's another thing. You can see over here phi mn. This mn is the unfactored moment. This is phi. So when we multiply, it decreases. You study that side of stuff? Not your thing? Cool. Okay, so there's a lot of things you can do with this. First of all, you can save it, obviously. You click save, and it goes where it goes to see users, my name, wherever I store my documents, and under a folder named conc, it is saved under the name of the project.xml. Let's take you there. Let's see what this place is like. So I go to my documents folder, and there's a folder named conc. It's going to be made automatically. And there's this XML file. I'm going to open it. Let's see what's inside. There's garbage. If you know what XML is, you know what this is. If you don't know what XML is, this isn't for you. You can share this file with anyone, and he or she will be able to open this in this program directly. We'll get back to that in a minute. So let's say you want to save all of this stuff because you don't want to lose anything. One, we already saved it, so we can open it for it later. But what do you want to share the reports and stuff? Well, first of all, I want to show you that we can save the image, this image, in a higher quality. Let's say I want to save it. So it says that it's saved in the exact same location under a folder named images, and with the same name .png file. Okay, let's see what we got there. Images and tutorial. So what else is left going on in life? Damn, I hate hard disks. Oh boy. Okay, final. So as you can see, it's quite a high quality image. You can crop this thing and paste it anywhere. The pixel density is enough for you to use it anywhere. The one thing out of the way, you can also save it as a PDF report. Now this is something new I added to it. So when you save it, it asks you how you want to save it, what name you want to give it, where do you want to save it. So let's go with tutorial for the time being and click enter. it's asking me if I want to save the iterations. Let's go with yes. It says PDF report of tuner saved at the same place under the name of tutorial.pdf. I'm going to click OK. And let's go back to conc tutorial. Okay, here it is. I'm going to open it, and here we go. Voila. So the report has your name, project name, the value of E, the value of total depth, the steel reinforcement yielding strength, and compression strength, blah blah blah, a lot of stuff. It has your results. Read this, pause the video, and it has all the shapes you wanted. For example, it has the rectangulars. Remember, the top and bottom width are the same. In the case of a trapezoid, they're different. In the case of a circle, the dia is the only thing you need. So that's that. And then there's the iterations. It all goes all the way to the end, 126. Pretty useful if you ask me. Another thing is that you can save this to Excel if you want to manipulate the data. So let's say I want to give it a name, tutorial Excel. It's saying it's saving it, and going, and saved. So let's go to conc. We have tutorial Excel. I open it, and we have all of that iterations and stuff. With I want to go to formatting. You can change. The main point here is that you get all of this data to manipulate for yourself. You can do that. So I'm going to save it and close. So that's all for now. You can change a lot of stuff. Do that for yourself. So let's go back to the slideshow. Okay, here we are. Reports and images. You already know that. So what it wants from you. As a developer, reserve all rights to change or sell the software. However, if you're a student and you want the libraries for all of this, for this stuff, I can give it to you. Just send me an email at this email from your own institutional email. Please don't use personal address. I know students have institutional emails. Use those, and I'll give you the GitHub files for you to use in your own software. It's cool. Let's see. Okay, credits and references. I've used iTextSharp, the DLL by these guys in making the PDF reports. I've used the equations from Reinforced Concrete Mechanics and Design 6th edition by James K. White and James E. McGregor. These are the equations I use to make the software. And of course, obviously, ACN 1311, American Concrete Institution, their committee, and their own standards. So let's go ahead. Okay, that's it. So if you have any questions, send me an email at this place. I'm going to be uploading the software in a few days or so. When finally bugs are over, you always saw a bug. So when that's over, I'm going to be uploading it to my Softpedia website. It's not my website, but I'm going to be adding it to it if you don't want to meet. If you have any other questions, do not mind sharing. Okay, bye.